For my Patreon viewers, here's a look back at one I did a few years ago on some black and white security cameras. The raw footage, including me burning up a tube. Enjoy. Okay guys, don't really have a lot to show you today. I've got a couple of old vintage video cameras here. These are from before the CCD or CMOS cameras were invented. These are actually black and white cameras, and well, if we pan the camera up to show the monitor, you'll see me on the monitor. They weren't very good. Quite noisy, the picture. They would overexpose quite easy, and generally, I mean, these ones were, well, these are very old cameras by today's standards. But this is how all cameras work. The color ones were no different. Color cameras came in two flavors: a single tube pickup and a 3-tube for broadcast cameras. And some of the really ancient ones used 4 tubes. They used an image orthicon for the luminance channel and a red, green, and blue pickup. But this is based on a Vidicon tube. This is a Vidicon tube. And basically a Vidicon tube is the camera equivalent of a picture tube. See, in your conventional CRT picture tube, your electron beam scans the phosphorus coating at the front end of the tube to create a picture. Well, in a camera pickup tube such as this, the image from the lens is projected onto the target area here, and the beam scans the backside of the target. Now, the target is charged to a high voltage through this metal conductor on the surface of the tube. In behind the glass is photosensitive resistors. They're connected to the target. It's just a uniform coating of a, like barium oxide or some type of material which is sensitive to light, will change its resistance when light hits it. As the focused electron beam, which is magnetically deflected, scans the surface of the tube, it creates a voltage difference because the beam is negative, whereas the positive is applied to the target. So the negative electrons will discharge the target. The brighter the image that's projected onto the target, the less resistance is created in the photoresistive coating, which will cause more current to flow, more electrons. It'll appear as a lower resistance, and it will drop the voltage on the target. As the beam scans back and forth, depending on what is projected onto the inside of the target, it will create an analog waveform that is the video signal. That signal is amplified, the synchronization pulses are added, and you get your composite video output. And this is what the inside of one of these cameras looks like. This is actually the one that's operating, and you notice this thing, I don't know if you can see on the back here, this camera requires 24 volts, and you're looking at, it's plugged into an AC outlet. See, it says AC 24 volts here. This is one that's designed for connecting to a low voltage transformer, where you'd have one transformer and it just used like bell wire to wire them all up. That way you didn't have to, if you're putting in a closed circuit system, you didn't have to pull AC to every location where you were going to mount a camera. You could just run some standard alarm wire, standard bell wire as it's called, to each location, and a coaxial line for the return video. And that way they didn't have to pull permits and stuff. If you were putting closed circuit system in a commercial building, you didn't have to pull electrical permits to have outlets installed. They could just use one transformer and run a bunch of cameras. Still done today on a lot of the cameras now. You go to Costco or any of the places and you buy a DVR with 4 cameras. You'll have one power supply and it'll feed all 4 cameras over the Ethernet or over the coax or whatever they're using anyway. This is very old. This goes back again to the I don't know what year this was made. Does it say on here? It's either going to be, I think there is a date on here. Can we read it? Can we read it? Probably not. Is it going to show up there? What does it say? 83 maybe? Oh, this one's actually a little newer. This is 89. So this camera, the one that's working, is actually newer. This one here, this old Ikigami, this was about 1982, I think, was when this one was made. It's extremely old. I've had this one since it was new. When I was in high school, my electronics project was I built one of these cameras from scratch. Made the circuit board, wound the coil by hand, the magnetic pickup coil, wound the yoke coils by hand, and made a yoke out of pieces of cardboard tubing. Wound all the coils around it, mounted it in. It was quite the little project, and I had the camera. I was quite proud of my creation. I had it at my parents' house, hanging up, pointing at the front door, because what else would you have a security camera for, right? Well, someone decided they liked it better than me, and they came down one night and took it. So it was replaced with this camera. And that camera served me well for many, many years. This one doesn't work now. This one still works. This one was given to me, old friend of mine when he was a jeweler. Or he is a jeweler, not was, he is. And when he upgraded his office cameras, this is one that he had at his, I think it was in his waiting room. So he just said, "Here, take it. You can have it." Dropped it off at my front door. So now we're using this as a piece to look at. But this one still works. The other one doesn't. So I'm going to hook up the cable to the other camera here. It's been sitting turned on for a while. I was hoping maybe it would warm up and something would happen here and we might get a picture, but we're still just looking at a blank screen. I don't know what the problem is. So I'm going to fire up my little scope here and we'll probe around on this thing and see whether it's something minor that's just for the heck of it. We'll see what's going on. These things require signals just like a TV. They generate sync signals and drive the tube. So let's just take a look and see what might be causing the problem on this thing. Okay, I got some test equipment hooked up to it now. We're just going to take a look and see if there's some of our voltages are present. So let's look at our 12 volts unregulated, and it's there. We have 15 volts. You can see that on the meter. So we know that the 12 volt supply from the transformer is working. There are all kinds of other voltages on this thing that need to be correct, and there are some fairly high voltages. We have a 500 volt supply, but we have like 2.3 volts on it. So we know where the problem already is. Same with the 300 volt supply. It's only got 2 volts. The 20 volt supply here, it's got like 7 volts on it. That's low. Minus 100 volt supply, it's got minus 0.2. So our problem is going to be in our horizontal oscillator section, which is because this is our transformer here. This is our it's like a flyback transformer, but we don't need the 10,000 volts that a picture tube needs. We only need 500 volts, minus 100, plus 500, plus 300, etc. We have a transistor down here, Q202 on the board. This is going to be, I believe, the horizontal output transistor, if I'm not mistaken. It's that one right there. Looks kind of like it's been warmed, doesn't it? And this may be the problem right here, this little transistor. just going to put my scope on here and take a look and see if I've got any waveform. So I put my scope on the base, and oh yeah, I've got an oscillator here. If I pan the camera up, you'll see that there is a waveform. So the oscillator is working, but I go over to the collector and I've got no output. See that? That should be a much higher level signal than the base drive, but there's nothing there. So I think this transistor itself might be foobar. So let's just turn the power off, and I'll just test this transistor with my DVM. I'll test it in circuit before I remove it. It might just be something as simple as a blown transistor. And if it is, I don't think there's anything special about this transistor. I might even have one that I can put in there just for the heck of it, just to see what will happen if it will actually make this thing work. You know, not that I need the camera for anything, just for the heck of it, right? Just to show you guys how these things work a bit. So if I test the transistor, yeah, this one looks like it could be shot. I got between my emitter and my collector, it's showing 0.2. It's showing a short, you see. I don't know if you can see that or not on the meter, but it's showing 0.2 across it. So this transistor itself may be bad. I'm just gonna pull the transistor out for the heck of it, and we'll see. I'll measure it out of circuit, because we could be looking at some loading in the circuitry that won't load it down. So let me just warm up the soldering iron and remove this thing, and we'll see if this is what's wrong with it. So here's a look at the bottom side of the circuit board here. This is the transistor here I'm going to take a look at and see if it's bad. To say, these are pretty simple designs. There's not much to these. You've got your oscillator and your output transistor, and it drives this transformer here. Generates the higher voltages that are rectified here, filtered in some of these capacitors. That gives you your pickup voltage for the Vidicon tube. So I'm just waiting for the iron to warm up here, and then we'll pull this transistor out and just take a look and see whether. Kind of looks like it's been hot, right? If you look at the board here, it's the board is kind of discolored. So this has been hot, and looks like there's been some modifications done to this thing. There's been a light added to it. LED's been stuck in the front. I think that can go. I don't think we need to have that in there anymore. Just another wire getting in the way. But yeah, we'll wait for this thing to warm up and remove that transistor and just see whether that will breathe some life back into this old camera. So I pull the transistor out, and it's testing bad. I just got to look this thing up and see what the heck this is. It looks like an ECG 186. It is. This has been replaced before. ECG 186. I don't even know what that is. I got to look that up. That was a cross-reference one, but it's got leakage all directions. So I'm just gonna go look this up and see what the heck this transistor is, whether it's just a generic NPN or PNP, and see if we can find one that we can put in here and see if this will make this thing work. So looking up the data for an ECG 186, it just shows as a general purpose audio transistor, NPN, which I don't have, but I do have a 2SC 4130. This is a much higher grade of component. This is a high-speed switching, high voltage, high-speed switching transistor that was used in, these were used in the Panasonic VHS switching power supplies. They were very common. I used to go through hundreds of those things because some capacitors would dry up and it would blow up it would cause the voltage to rise to the point where Panasonic, interesting story about Panasonic. I could tell you all kinds of stories about electronics and the problems that we used to have with them. Panasonic, back in the early 80s, didn't put protection in the secondary stages of their power supplies, and when the voltage went too high, everything went boom. It had opened up the top of a VCR, and all the components, the tops were blown off all the ICs, and okay, the things are right off because the voltage would go through the roof. So they solved that problem by putting a Zener diode as a crowbar on the 12 volt rail to stop the 12 volt rail from going to like 300 volts. And when the power supply started to go high, it would the Zener diode would conduct, and it would continue to conduct until the output transistor the chopper transistor, this thing, would overheat and blow. So we used to rebuild a lot of power supplies, change a lot of Zener diodes, change a lot of the regulators, the chopper transistor, change a lot of capacitors, and change a lot of Zener diodes. So this is the same basing. It's base collector emitter. It's an NPN. If we look at this one here, you'll see I got lights shining on my to measure a transistor. Okay, this is NPN, so we put the positive lead on the base of the transistor, and I'm just going to zoom the camera out a bit here. We have conduction, 0.5 volt drop, right? That's base to collector. Again, base to emitter. Again, about a 0.5 volt drop because it's a between 0.5 and 0.6 silicon transistor, right? If we reverse the polarity, we'll have infinite readings from the base to the emitter and base to the collector. And of course, emitter to collector, we'll have infinite readings. You see that? Whoops. Now this bad transistor here that I was using, again, it's, well, you'll see. I got a reading there at 0.6. That looks okay. I got a reading there at 0.6. But I reverse the leads, and I got a reading. See, the transistor's leaky. And between emitter and collector, I have a reading. Transistor's gone leaky. That's the bad one. So I got a good one here. I'm just going to clear some solder off these holes here. We're going to mount this thing and see if it actually makes this camera work. That'll make my day if I fix a 30-year-old camera, right? There's a reason why I didn't show you guys me threading the holes here, because the air was blue. I was cursing because I can't see the holes. It's one of the problems when you get older, is that your eyes don't work quite as well for seeing this close-up stuff. And I find myself using magnifying glasses and reading glasses and stuff more and more when I'm working on electronics. I wouldn't say it's the reason I left the business, but it could very well be one of the reasons, is that I was starting to find that the really small traces were getting harder and harder to see. And this one isn't even that particularly that small. These are fairly big by the standards that we see today with some of the stuff, that it's just incredibly small. I remember when I was in the business one time having to change an IC that had, it was a flat pack. It wasn't a BGA or anything. It was just a regular flat pack IC. And I think it had, could have been 200 pins, 50 pins per side. That sounds about right. It was an LSI 4-sided flat pack, and maybe it was 40 pins per side. It was a lot. It was a lot, and I was having to. What we used to do is we used to take a piece of steel wire and slide it underneath the IC, and flow some solder onto it. Stainless steel wire, solder won't stick to. So we would we'd first of all coat everything with solder, short them all together, and stick this wire underneath the flat pack, and then heat it up so the solder was hot on all of them, and then just gradually pull the wire out, and as heating it, lift the wire up and bend all the pins back at the same time. And do that on 2 of the sides, or 3 of the sides, and then the 4th side just heat it up, and the IC would generally just fall right off. And then you could go back and clean up the board, put your flux on it and stuff, and prep it for the new IC. Okay, the moment of truth. I've got everything hooked up. I haven't switched it on yet. I'm just going to put my probe on to the to one of the high voltage sides, maybe the 500 volt supply. Try and turn on the power with one hand here, and we'll see what happens. Oh, I got 449 volts, 450 volts. See that? I think our oscillator's working now. Let's see if we get a picture on this sucker. Pan it up to show the screen. Okay, we have a picture. Wow, it's out of focus, but we have a picture. See if we can make that better. I'm just going to tweak the beam and the target controls and stuff on here. See if we can get that thing looking a little better than that. It's definitely out of focus, but that could be just because the beam is not set up. And the focus is not set. Where's focus? Oh, look at that. There we go. Beam. Target. This tube's actually in really good shape. Just close down the iris a bit here because we're kind of overexposed. And we'll just adjust the focus on the tube. Look at that. Wow. That's actually not bad. It's better than I thought it would be. I don't know if this thing's going to work any better if I zoom the camera in. The problem with these modern cameras is they use a variable speed shutter. When the picture is too bright, you can see it. It's a rolling shutter. See that? The rolling shutter is causing some artifacts. That's not how the picture looks on the screen. That's just the artifact of the rolling shutter on this CMOS camera. Focus. And the beam current. How you adjusted these cameras was you wanted to have minimal beam current because too much beam current would shorten the life of the tube. So you wanted to have minimal beam current, just enough to discharge. There we go. Just enough to discharge the tube. Same with the target. You don't want the target too high. There's a few burn-ins. You can see a few burns on the surface of that tube. And I wonder if I should go get a laser and really burn it up. I'm sure if I shine a laser in here, we'll do some damage. What do you think? You want to see me damage this tube with a laser? Maybe I'll damage the other one. This one looks better than the other camera. This one actually has not a bad picture on it. Oops. And I thought maybe the pickup tube would be bad, but apparently not. This one actually works. We're getting some interference on here because I don't have the case on it. So without the cover on it, it's not shielded, right? So, but yeah, you know, I mean, it works. I'm very impressed that this thing, after all these years, actually still works. I have the cover for this camera too. If I put this case back on here, I bet we'll get rid of. Oh, I better make sure that before I do that, I better make sure that my leads for the transistor I just put in are cut off. I'd hate to short them up against the case and blow up the camera that I just fixed. So we're just going to clip the leads off here, and I'll put the cabinet back on it, and that should make the picture look a little better. Might even have some screws that I can attach to it. There, that looks a little bit better. I know that the camera I'm using to pick up the monitor there, this little video camera, we got the rolling shutter we got the rolling shutter artifacts on there, but other than that, it actually looks presentable. I'm just putting some screws back in the cover on this camera because this is a kind of an antique, this thing. It's almost a museum piece. So I'm going to just put the case on it and throw it back into my junk box where it can be forgotten about for another 20 years. Of course, wouldn't you know, all the screws that I've got here are, I got the wrong bit in my driver. There, that one might work. Of course not. There, that one will hold it together. Maybe not. I think that screw might have been a little too long. I think when I was tightening that down, I saw the picture change, so I think that one might have been a little bit too long, and I was shorting something out on the board. So I'll have to put one of these short screws in, but I just can't find the right. This is like a Torx bit on this thing, and I don't have the right bit for it. I'm sure I've got some more screws around here. So there you have it. I got the camera back together. It's working. Good old Ikigami, what is this one, an ITC 40. Good old Ikigami ITC 40 closed circuit security camera from the early 1980s. Back up and running. And the picture is actually not bad at all. Probably as good as it was when it was a lot younger. Hope you enjoyed this one. Now, the dilemma. Should I blow up the other one with a laser? I think I will. Let me go get a laser and see what it does. I have a laser. Have laser will travel. I don't know if I want to point it into this camera or not because I'm afraid I might blow up this camera. I've done that before. My last video camera, I created some black spots on it by accident. So let's see whether we can damage this pickup tube. This pickup tube actually looks to be in pretty good shape. Maybe I shouldn't do this, but in the name of science, we need to do this. Oh yeah, we did it. I just created a black spot right here. I just did another one. There you go. That's how you blow up a camera pickup tube with a laser. Didn't take very long either, just a little flash. And now we have a permanent spot. See that? Now we have a permanent spot on that pickup tube. And this isn't even a particularly bright laser. If I brought my green laser out, I'm sure that would do considerably more damage than this one here did. Yep, we burned it. So there you go, a little laser pointer. It's deadly, especially to old cameras. Now, I do have a more modern camera. I wonder if we can damage that. I don't even know if this thing works. I've got a number of these little pieces of crap. I don't know if anybody remembers these things. Little citizen CCD cameras, black and white. I wonder how one of these would be for blowing up. Well, we're not going to do that this time, but for a future video, maybe. Again, the same chap that gave me this gave me a whole bunch of these things. He just said, "Here, take them." I don't have much use for black and white cameras from, you know, the 1980s, 1990s, but maybe worth experimenting with. Anyway, hope you enjoyed the repair of the Ikegami ITC40 and a look at this old Hitachi. I think it's a Hitachi. Look at this old Hitachi camera that requires 24 volts AC. I've actually got it plugged into a line cord, which is plugged into my Variac, which is set for 24 volts, as I didn't have a 24 volt transformer. So I've got this thing running kind of Mickey Mouse just to demonstrate it here. We'll be tearing this thing apart momentarily. And I hope you enjoyed it. We'll make some more. Later, eh?